Hi, my name is Bill Whitman. I'm a co-author of this book, Refrigeration and Air Conditioning Technology. We wrote this book to provide students with a practical, service-oriented text. The information in this video series will provide actual troubleshooting situations and service procedures for air conditioning systems. Bill Johnson is the other co-author of this text. And throughout the series, Bill will be discussing several typical service calls. We'll also take you on-site to see some real-life troubleshooting. There you'll have an opportunity to see where theory meets practice.
Despite the complexities of today's air conditioning problems, most of them are involved with either being mechanical or electrical in nature. So therefore we use two different types of instruments to troubleshoot either mechanical or electrical problems. For example, mechanical problems. This is one of the items that we would use to troubleshoot mechanical problems. Anybody hazard a guess?
A gauge manifold.
Gauge manifold, that's very good. How about this one?
That's a 4-lead temperature tester.
4-lead temperature tester. Very good, very good. These are used to troubleshoot mechanical problems. Now, when we get to troubleshooting electrical problems, we use a different set of tools. This one, for example, is?
That's a VOM.
A VOM, which stands for volt-ohm milliamp meter. This is an analog type meter because it has a needle. We also use, in the VOM meter types, we use the digital VOM, which would read out in numbers. Another electrical instrument that is common is the clamp-on ammeter. This one can also be used to check voltage with. Now, while using these instruments, we must be very, very careful. We must be conscious of safety, very conscious of safety. The first person that you want to save and the first thing you want to save is you. When we handle high-pressure refrigerants, we are either handling them in the liquid state or the vapor state. In the liquid state, we're subject to burning our fingers severely and from freeze burn. We should always wear goggles and gloves when working with refrigerant in the liquid state. In the vapor state, you will not be able to burn yourself, but you would be subject to blowing debris in your eyes, so you would always want to wear goggles while handling or transferring liquid refrigerant in the vapor state.
Two types of pressure connections are used, the Schrader valve and the service valve. The Schrader valve is a pressure connection only. The service valve can be used to isolate the system for service. The system might have a Schrader connection for the gauge port and a service valve for isolation. The technician carefully threads the knurled connector onto the low-pressure Schrader port with a minimum of refrigerant loss. Notice that he is wearing gloves and goggles. The high-pressure connection is made in a similar manner, except that a small control valve is used on the end of the line. With this valve, the technician can control the actual depression of the Schrader valve. Notice that pressure does not register on the gauge until the valve handle is turned. This valve will be used to save the refrigerant in the high-pressure line when it is disconnected. Without this valve, the refrigerant in the high-pressure line would be lost when the hose is disconnected. The loss could be enough to alter the system charge. The technician then purges the gauge manifold through the center line.
Let's take just a few moments and talk about how the service technician would use the gauge manifold and what the technician would use it for. Printed on the front of this gauge, we have a lot of numbers, and they can be confusing to you. On the outside edge, in black, we have printed the pressures that we would indicate in the system. Printed on the inside, we have numbers that are temperature corresponding to those various pressures. The temperatures correspond to three basic refrigerants that are commonly used in the field, R502, R22, and R12. In the air conditioning field, R22 is the refrigerant that we would find to be the most common. This is the low side pressure gauge on the left-hand side that we would use to indicate pressures on the low pressure side of the system. On the right-hand side, we have the high pressure gauge that we would use to discover and indicate pressures on the high pressure side of the system. Now this relationship of pressure and temperature is called the P&T relationship. Many technicians find it convenient to use a pressure-temperature relationship card that folds up and goes into their pocket. Many technicians feel it convenient to use the numbers on the gauge manifold. In the classroom, we often use a chart the size of this for instructional purposes. The chart actually reads out the same way as the gauge manifold or the pocket card, only the chart may have some more refrigerants listed on it, such as R717 ammonia and R500, such as on this chart. Now, the way the service technician would use this chart, for example, let's take a head pressure example. Suppose that your head pressure for an R22 system is running 296.8 pounds per square inch gauge. If we looked directly to the left, to the white column here, we would see that we are condensing the refrigerant at 130 degrees Fahrenheit. Now, you should be able to find the same thing on your card. You'll notice that this chart is marked off in colors and that we're using the green column. Each one of these colors designates the color assigned to that particular refrigerant. Green is the color that's assigned to R22 as its refrigerant color, so that anytime you see a green refrigerant drum, you would know that you are looking at an R22 refrigerant drum. Are there any questions? Jack?
Can you always tell the refrigerant temperature if you know the pressure?
Yes, Jack, as long as you know what the refrigerant is, the identity of the refrigerant, and as long as the refrigerant is standing static in a cylinder, such as in storage, or it's boiling in an evaporator, such as in an operating air conditioning system, or if it is condensing in the condenser in an operating condensing system in an air conditioning system. Are there any other questions? Okay, let's go to a video.
A dry bulb wet bulb reading is taken to determine the humidity. A cotton sock with pure water is placed on one of the temperature leads. This lead may now be used as a wet bulb indicator. A wet bulb and dry bulb reading to determine the relative humidity and the latent heat load on the coil may be obtained by placing a dry bulb temperature lead next to a wet bulb lead in the return air stream. The velocity of the air will be enough to accomplish the evaporation needed for the wet bulb reading. When the evaporator supply air temperature needs to be obtained, a temperature test may be used. The supply air temperature will normally give a dry bulb reading about 20 degrees Fahrenheit lower than the return air temperature. This is known as the dry bulb temperature drop across the evaporator coil. A temperature lead can also be used in conjunction with the suction pressure to determine superheat. Convert suction pressure to refrigerant boiling temperature. This boiling temperature can then be subtracted from the suction line temperature to determine the superheat. The suction gas might be part of liquid if the filters are stopped up or the evaporator coil is dirty. The temperature of the discharge line might indicate that there is a problem inside the compressor. If there is an internal refrigerant leak from the high pressure side to the low pressure side, the discharge gas temperature will rise above normal. A liquid line temperature check will determine the subcooling efficiency of the condenser. According to the thermometer, the outdoor air temperature is 79 degrees. This condenser is clean and is a medium efficiency condenser. 30 degrees Fahrenheit is added to the ambient temperature of 79 degrees, equaling 109 degrees. According to these calculations, the refrigerant should be condensing at around 110 degrees. The head pressure should be about 220 psig, according to the pressure-temperature relationship chart. 226 psig corresponds to the 110 degrees Fahrenheit for R22. This is the closest value to 109 degrees Fahrenheit on the chart. The head pressure reading is 220 psig, very close to the calculations you have just seen performed. According to this information and the pressure-temperature chart, the design suction pressure is 40 degrees Fahrenheit. This would correspond to 68.5 psig on the P&T chart. Because the outside temperature is only 79 degrees, this unit does not have a heavy load on it. The head pressure is well below the design pressure for a 95-degree day. An estimation would put our suction pressure at about 63 psig. Our actual reading is 63 psig. These calculations are used to check the refrigerant charge in an air conditioning system. The approximate head pressure can be found in this manner. The suction pressure can be estimated. These methods should only be used, however, when the manufacturer's data is not available. Some manufacturers will have a charging chart attached to the unit or in a book for the unit. This chart will give you the pressures that correspond to the operating temperatures. Here is another form of charging chart you might see in the field. Some manufacturers don't provide charging charts. Certain rules apply when you use a charging chart. Both indoor and outdoor coils must be clean, and you must take the indoor wet bulb temperature. This determines the latent heat load on the indoor coil. You must also know the outdoor ambient temperature before you can use the chart. The manufacturer will specify the boundaries for the head and suction pressures for a given situation.
The 4-lead temperature tester, of which I only have one lead connected into this particular tester, is one of the very popular instruments that we use in the field. Reason being is because it's very accurate and very fast to respond. I'm going to turn this one on. First we get 888. Now we're recording room temperature. Now watch what happens when I hold the lead. Watch the response time on this. This instrument is used for several service procedures in the field. One procedure would be to clamp the lead on a line in order to determine what the temperature of the refrigerant inside the line would be. This is used for determining suction temperature, suction gas temperature, and for determining liquid line temperature. On the suction line, we're trying to determine what the superheat might be with the refrigerant. On the liquid line, we're trying to determine what the subcooling would be within the liquid line circuit.
Often, a technician can verify a power supply to the system by starting the indoor fan instead of using electrical test instruments. This quick check can save a trip under the house or up to the attic if the fan will start with the fan relay. Several things are apparent. The indoor fan is working. This means that there is control voltage and there is line voltage to the unit. As with gauges, the experienced technician will follow electrical safety precautions. Many times, a system will need to be inspected while the power is on. Use only insulated meter leads to touch hot terminals. These meter leads have stops to prevent the technician's fingers from sliding up and touching the terminals. Special care is taken when troubleshooting the main power supply panel. A screwdriver or other tool is never used in the energized panel. Various circuits are followed to ensure power is getting to the components. If the compressor is not running, the compressor circuits must be checked. Here is where an electrical diagram can be very useful to you. It can help you work safely.
We oftentimes find when we're troubleshooting mechanical problems that we get into electrical troubleshooting also. After all, what controls the unit? Electricity. What stops and starts the compressor? What stops and starts the fan motor? Electricity. When we have a mechanical failure, electrical components are what would cut this unit off to save the unit as safety controls. Now we must remember anytime that we're troubleshooting that you have to have 3 things present. You must have a power supply, you must have a path for the power to run on called a conductor, which would be the wires, and you must have a load. Now in our example we're using a generator as a power supply, we're using wires as our conductor, and we're using a light bulb in our load. Now when we get out into the field and we look at this mass of wire and so forth in this unit, we have a tendency to get confused. We need to be able to tie this theory of power supply, conductor, and load to practical use by realizing that the power enters this unit on these 2 wires right here. The power continues down the wire or conductor to the power-consuming devices, which would be called the load. This load here is the compressor. It actually is the major load device in this unit. Also, we have another load up here, which is the fan motor, the condenser fan motor. These are the 2 power-consuming devices, or the load, in this unit. Every system will divide itself up into circuits and sub-circuits that will consist of a power supply, through the path or through the conductors, to a load. The load is also known as the measurable resistance. The VOM, volt ohm milliamp meter, is also used to check individual components. Here on the bench we'll show you how to check a couple of the very common components that we work with out in the field. This is a simple compressor contactor, often called a relay or a contactor. This contactor actually has two basic types of circuits through it. It has one circuit through the set of contacts, or sets of contacts, that passes power. Power comes in, power is supposed to go out. This circuit, whenever the coil is energized, should close the set of contacts. The coil circuit is actually considered a load circuit. Now what we're going to do is we're going to test this relay out using the VOM. First thing I'm going to do is zero the meter. Then I'm going to attach the leads from one side of the relay contacts to the other. Now you'll notice that we have a reading of infinity on the meter. When the coil is energized, this is what would happen in the relay. The contacts would close and the circuit would go to 0 ohms resistance. This would be the sign of a good relay, a relay that you would use or reuse. Now the coil circuit might be checked in a different manner. To check the contact circuit, we checked it on the R times 1 scale. Now we'll have to experiment around and find out how much resistance is actually in the coil circuit. Now we'll fasten one lead to one side of the coil circuit on the relay. We'll take the other lead and fasten to the other side of the coil circuit on the relay. This is the information that we want to know about the relay. We have a measurable resistance through the relay coil, stating that if we did apply power to this relay coil, that power would be consumed and the relay should work from there. We've decided that this relay is good because we have continuity through the coil circuit, and then when we energize the coil circuit, we get continuity through the contact circuit. So we've decided this relay is good. Another component that we often check in the field, often need a check for in the field, is a capacitor. Capacitor is another component in the field that we oftentimes have to verify as good or bad, defective, good or defective. And the way we do this is we're going to take our meter leads, touch them together, zero our meter on R times 10,000. Our meter is zeroed. Now this particular capacitor is a start capacitor, and if you'll notice it has a bleed resistor in the top of the capacitor. All capacitors, if they are good, will hold a charge, and it will hold a charge strong enough that if you were to apply your meter leads to the capacitor, that it could do damage to your meter. This capacitor has a bleed resistor that will bleed the charge off of the capacitor between cycles. Other capacitors that do not have a bleed resistor, you would have to bleed them off by discharging the capacitor. Make sure that you do that, because if you were to apply a meter lead to a charged capacitor, you could do damage to your meter. We'll fasten one lead to this side of the capacitor. And watch our meter needle when we touch the lead to the other side of the capacitor. It's going to rise and fall. Now what's happened internally is the battery inside the meter has charged the capacitor, and then it has discharged partially again. That means that this capacitor will charge and discharge. Now if I touch the meter down to the same leads again, to the same terminals, we're going to get another discharge, another charge and discharge. This capacitor is capable of charging and discharging. Now what we don't know about this capacitor is the value of it. This capacitor is rated in microfarads. It says here 145 to 175 microfarads. This is a quick field check using an instrument that you would normally carry on your truck to check a capacitor in the field with. Two other things that might go wrong with this capacitor is this capacitor might have an open circuit. Now if the capacitor had an open circuit and we touch the leads down, this is the meter reading we would get. Infinity. No circuit through the capacitor. That capacitor would be deemed defective. Another problem that might occur with this capacitor is that it might have a complete short within from terminal to terminal. dead short. If this were to be the case, when I touch the meter leads to the two terminals, this would be the reading that I would get. 0 ohms resistance. No measurable resistance, no rise and fall from the meter needle. That capacitor would be defective. The only time that the capacitor would be considered good is when you get a rise and fall from the meter needle. As you move into the field of troubleshooting, you must become familiar with your instruments. Your electrical test instruments are safety instruments to you as well as diagnostic tools. This instrument will be used to check power before you put your fingers in it. So it becomes a safety tool for you. So become familiar with it. Use it, learn to use it, and learn to become familiar with it.
Learning about troubleshooting is an ongoing process. Your continued study of these electrical and mechanical aspects are essential to your success as you make the transition from the classroom to the field. Good reference books and manufacturer's literature will benefit this process, keeping students and instructors abreast of the newest technologies and procedures.